In many groups, the elements of the groups are matrices and the operations are usually matrix multiplication or matrix addition, and in this video we will see the matrix groups. Matrix group. Elements of a group can be matrices also. In this example we will see all matrix groups. And the operations will be the usual matrix addition and matrix multiplication. Let us see. A set is see, to show a set under a binary operation is a group, we must be familiar with this set and the binary operation. Then only we can prove the group axioms. So prior to showing anything, any set under any binary operation is a group, we must know this set and the operation properly. So what is this set? This is set of all matrices of order m by n. We have m number of rows and n number of columns, and we have all matrices, and entries are from the set of real numbers. Set of all matrices of order m by n with real entries. The elements in the matrices in this set are the elements from the set of real numbers. Let us take the operation matrix addition, that is component wise addition. We'll check all these four axioms. Closure for any two matrices. Suppose one is capital A and capital B are two matrices of order m over n with real entries. A plus B is also a matrix of order m by n and entries are from real numbers. This also belongs to, why? Because in matrix of addition, suppose let A equals to, I am writing in the element form, this Aij, this is the element of the matrix A in ith row and jth column, and we have the order m by n, and B is Bij. What is A plus B? A plus B is Aij plus Bij. So A plus B is also a matrix of order m by n. This is the definition of matrix addition. We'll just add the component wise elements of the two matrices. First one is A and second is B. And Aij is ith row and jth column entry, and this is ith row and jth column entry of the matrix B, and we will add them. So this belongs to, and the entries of the matrix A and the matrix B, these elements are from the set of real numbers, so their addition is also a real number, hence these elements also belongs to the set of real numbers. So we have closure property. So closure property holds. What about associativity? Let me erase it. Huh? Associativity. Let A, B, C be three matrices with entries from the set of real numbers. What is A? Let A is Aij and is Cij, small Cij, M over N. We have A plus B plus C equals to Aij M over N plus Bij M over N plus Cij M over N, and this is same as Aij plus Bij M over N, and we have Cij M over N, which is same as Aij plus Bij plus Cij M over N. Let me erase first two lines. Now what we have? This one, Aij plus Bij plus Cij. I can take common. I can take Bij plus Cij in a bracket. Then we have Aij M N plus Bij plus Cij, which is same as this is capital A, this is plus, and we are done. Associativity. A plus B, add A plus B first, then C. It is same as keep A, then add first add B plus C, then add that with A. So associativity holds. And now we see identity. We have zero matrix. This capital O denoted as zero matrix. Zero matrix of order n by n. So this matrix is in this form. Every element are, every entries are zero. M rows, n columns, and all entries are zero. This zero matrix. For any matrix A of order m by n from entries of real, if we will add A with this zero matrix, we will get A. Also zero matrix with A is A. Therefore we have identity, and identity is zero matrix. And let me erase it. What is the inverse? For inverses, let me use another color. Inverses. For inverses, for any matrix, we have its negative matrix, which is, suppose A is, its entry is Aij, then minus A has entry minus Aij, and when we will add A with this matrix minus A, we will get Aij plus minus Aij which is m by n, 0, which is 0 matrix of order m by n. So we have identity for every matrix in this matrix set. So we are done. This is a group under the operation matrix addition, and moreover this is commutative. This is a commutative group. Commutativity. For any two matrices, we have A plus B is same as B plus A. Therefore, this is also an abelian group. Note it down. I will erase. Suppose we have the same set, the set of all matrices of order m by n with entries from the set of real numbers, and operation I will take operation is multiplication. Will it form a group now? See, suppose we have m is 2 and n is 3. Suppose we have 2 by 3 matrices. Suppose A is a 2 by 3 matrix, and another matrix is B of order 2 by 3. Is the matrix multiplication possible in the first step? Can we multiply A and B? No, because the number of columns in the set in the matrix A should match the number of rows of matrix B. Here number of columns are 3 and number of rows are 2. 3 not equals 2, so A times B is not possible. It's not possible. So this operation is not a binary operation, and this is not an operation on this set. So what about if we will take m and n are same? Suppose this set is the set of all, this is the set of all square matrices of order n. Now we have a matrix multiplication. Take any two square matrix of order n. Order n means this is a square matrix, so your number of rows and number of columns are same. Suppose A is a square matrix of order n and B is a square matrix of order n. Now we can multiply A and B. So all square matrices of order n under the matrix multiplication satisfies closure property, because matrix multiplication is possible, and the product you will get, that also has order n, and that is also a square matrix. Let us see this one, this example. Suppose we have the square matrices of order n and the entries are from real numbers. Closure property will hold. Why? Take any two matrices of this set, then its product is possible, and A times B also belongs to the set of matrices, square matrices with the entries from real numbers, because the entries of A and the entries of B are real, and if we will multiply them, the product we will get, that will be also a real matrix of order n, square matrix. Associativity, matrix multiplication is associative. So A times B times C is same as B times C. Matrix multiplication is associative, hence associativity property will also hold. Identity, there is one identity element, that is identity matrix itself. Identity matrix will work as identity here. Identity matrix of order n. Identity matrix has all diagonal entries 1, and we have n number of ones, n ones, and all are 0. So identity matrix will work as the identity element here, and identity matrix has diagonal entries 1, and other entries from the diagonal are 0 elements, and this will work as identity because for any square matrix of order n, we have identity times that square matrix is same as A, and A times identity matrix of this is. So identity matrix works as identity element. What about inverses? Inverses, do every square matrix has inverse? Answer is no. Suppose we have, for example, suppose we have square matrices of order 2, entries from real, and let me take 1 0 0 0, this matrix, or the best example is 0 matrix. These are not invertible. There does not exist any matrix, square matrix of order 2, and which will multiply with this matrix and will get identity back. There does not exist. Does not exist any. Does not exist any. So for inverses we will write. Let me erase the first 2 lines. Operation is multiplication. Operation multiplication. So 0 matrix, square matrix 0 has no inverse. This matrix also has no inverse. A matrix can't have inverse if its determinant is 0. If a matrix is singular, it will not have inverse. So let us remove those matrices whose determinant is 0, and let's see if that will form a group or not. And that has a special name. Let me erase it. These are not groups. This is a special name. G L N R. This is called as general linear group, and operation here is multiplication. Operation is matrix multiplication. The set contains elements. The set of all n by n matrices with determinant non-zero. These are non-singular matrices, and we will show this is a group under the operation matrix multiplication. First one is closure. for any two matrix belonging to GLNR, we have, suppose A and B, two matrices belong to this set, then we have determinant of A, this is determinant of A is non-zero, and determinant of B is also non-zero. So what about product A times B, its determinant? By the property of determinant, determinant of two product is same as the product of its individual determinants, and since this is non-zero and this is non-zero, their product is also non-zero, and hence this A product B also belongs to, because they are non-singular matrices. What about associativity? Associativity will hold because matrix multiplication is associative. Matrix multiplication is associative. Take any three matrices is associative. Take any three matrices. This happens for any three matrices, any three square matrices of order n. So this will also happen for matrices belonging to this set, matrices having non-zero determinants. So associativity will also hold. Now let us erase. Please note things. You can pause the video to note. Associativity. I will erase this line also. And what about identity? As identity matrix. Identity matrix IN will work as identity, because this also belongs to the set GLNR, because this has determinant 1 which is non-zero, and times any matrix belonging to this set is A times for all matrix belonging to GLNR. And inverses, these are singular matrices, so its determinants are non-zero, and therefore its inverses exist for every matrix belonging to this set. For all matrix of non-zero determinant, we have matrix A inverse, which also belongs to GLNR. Why A inverse belongs to GLNR? If A is non-zero, if A is non-singular, its determinant is non-zero, and A inverse has its determinant 1 over the determinant of A, and 1 over determinant of A is also non-zero. So this matrix also belongs to this set, and A times A inverse is equal to A inverse times A, which is our identity element. So we have proved this set under the operation matrix multiplication is a group, and remember this set is GLNR. This is general linear group. Suppose we have GL2R, we have all non-zero determinant matrices of order 2 by 2 with entries from the set of real numbers, and with matrix multiplication it will form a group. Is it commutative? Answer is no. Matrix multiplication is not commutative. Commutative. Let me erase these two lines. Pause the video to note. Commutative. A times B is not equal to A times B equals to B times A. It is not always. We can have the example of two matrices where this product is not equal to this product. If we will reverse the matrices, they will not be all. So this is an example of non-abelian group. We have a non-abelian group. Non-abelian. Let me erase it. We have another set of matrices. This is SL and this is read as special linear group. And this set is equal to the set of all matrices of order n by n with determinant equals to 1, and this will form a group under operation is matrix multiplication operation. Matrix multiplication. We will also verify this one. Closure. If two matrices A and B is in the set SLNR, if we have two matrices A and B in the set SLNR, then does their product also belongs to SLNR? The answer is yes, because if we have two matrices of this set, then their determinants are determinant of A equals to determinant of B equals to 1. Both are 1. Determinant of A and determinant of B is 1. If we have A times B, and this happens since determinant of A times B is equals to determinant of A times determinant of B by the property of determinant, and this is 1, this is 1, therefore they multiply to give 1. Since the determinant of A times B is 1, this matrix belongs to SLNR. Also the order of this matrix is n, because A is a square matrix of order n, B is a square matrix of order n, and the entries are also from real numbers. So their product entry will also have real numbers. Associativity will work because matrix multiplication is associative. Matrix multiplication is associative. See, associativity is a rule. For example, suppose every student of a college will wear uniform. Then the students of mathematics department will also wear uniform. Similarly, here also, since matrix multiplication is associative, take any bigger matrices, take all matrices, and if you can multiply them, and by the property of matrix multiplication, it is associative. So this is a smaller group. This is a smaller group of matrices, and the matrix multiplication will also be associative here, because this is a rule, and this rule satisfies for a bigger group, and this group, this set lies in that bigger set. What about identity? Identity. We have identity element I, and its determinant is 1. Since determinant of is 1, and a times in equals to in times a equals to a for all a belongs to SL n R. Please pause the video to note. Let me erase now. Inverses. Since this is a matrix with non-zero determinant, its determinant is 1. So its inverse will also exist, and there exists an inverse of the matrices which has non-zero determinant. So A inverse exists as a determinant of A equals to 1, which is non-zero. Also determinant of this matrix, by the property of determinant, it is 1 over determinant of A, and which is 1 over 1, which is 1. Therefore that implies this matrix will also belongs to SL n R. Hence it is a group under matrix multiplication, and we are done. And commutativity will not work, because matrix multiplication is generally not commutative. You can have example, you can find 2 examples of matrices A and B. A times B is not equals to B times A. So we are happy because we have done many examples in this video. So we are happy, and the bag of matrices which I will give to you is, let me erase this. In this video we have seen, previously we have the set of integers under addition, the set of real numbers, the set of rational numbers under addition, the set of real numbers under addition, the set of complex numbers under addition, the set of non-zero rationals under multiplication, the set of non-zero reals under multiplication, the set of complex, non-zero complex under multiplication. All are abelian groups. Now we have non-abelian groups. We have also abelian group. This is also abelian with the set of all matrices of order m by n with real entries. Operation is addition. And we have seen non-abelian group. Non-abelian group. Non-abelian. Let me use another color for non-abelian. GL and R, general linear group. It contains set of all matrices of order, square matrices of order n with entries from real, SL, and R. And there are many other groups. See, you can construct groups. Take any random set, take any random binary operation, and check whether they are satisfying the group axioms or not. If they satisfy all group axioms, then it is a group. If not, then it is not. Thank you. Thank you. This bag is yours.